Now we can also do a hypothesis test to test the hypothesis that X contributes no information in predicting Y. In other words, that's saying H0 is that rho equals 0 against the alternative that rho is not equal 0. However, that's just equivalent to testing beta 1 equals 0 against beta 1 not equal 0. So that's slope equals 0, slope not 0. Remember, slope is 0. Your y hat's just a constant. There is no variation in the y hat values with X. And we did that previously. So now if we did carry out that test, our null is that rho equals 0. For a one-tailed test, alternative is rho less than 0 or rho greater. This is what our test statistic looks like. That's actually beta hat over the standard deviation, actually standard deviation of beta 1 hat. And then we've got rejection region, similar to what we did before. And then the two-tailed test, the only difference there is your alternative is rho not equal 0, and then your rejection region is less than negative T alpha over 2 or greater than positive T alpha over 2. And then our test requirement is that the sampled X and Y values are randomly chosen from normal population. So that's another way to accomplish the same thing as the hypothesis test on the regression slope. Now, another alternate measure of model utility is something called the coefficient of determination. This measures the contribution of X in predicting Y. So let's say we've got a data scatter plot that looks like this. Now, if we assume that X contributes no information to predicting Y, so that means that the slope of the regression line is 0, then our regression line is just y hat equals y bar, which is right here. And remember, the sum of squares of yy is sum of y minus y bar squared. So the y coordinate of the point minus the mean, which is the y coordinate on this line. So if we assume that X does contribute information, then our y hat is going to be beta 0 hat plus beta 1 hat X. So then we get a line that has slope that's non-zero. And then our sum of squares of error here, this is the sum of the squared deviations, is SSE. So we're looking at the difference between using sum of squares of YY as the total squared error versus SSE. So SSYY is your total sample variability around Y bar, whereas SSE is the remaining unexplained sample variability after you fit the data to the regression line. So we're contrasting those two cases. So then your coefficient of determination, you take SSYY, there's more error there, and subtract off SSE. So that's what we would call the explained sample variability. And then SSYY, that's the total sample variability around the mean. So if we divide those two, we get the proportion of the total sample variability that's explained by the linear relationship. So our coefficient of determination, we denote that by R squared. It is SSYY minus SSE over SSYY, which if you split these apart over the LCD, you'd have SSYY over itself, which is a 1 here, minus SSE over SSYY right here. So just an alternate way to do the same thing. R is always going to be between 0 and 1. So R squared is also always between 0 and 1. And R squared is actually the square of the coefficient of correlation R. So in other words, when you compute this value, it's the same as just squaring our coefficient of determination. So let's look back at example 1 again. So again, we're relating medication dose in milligrams to pain level Y. We're going to compute and interpret the coefficient of determination. So here's our linear model. Here's our sum of squares. And then SSE we had previously figured as 1.440 to 3 decimal places. So I'm going to use this form. for r squared. So this will be 1 minus our SSE is 1.44. Divide by sum of squares of yy, which is 22.75. Let's compute that on the calculator. Notice r squared 0.93655 is what we got from the linear regression. So let's see here, 1 minus 1.44 divided by 22.75. And look, there's 9367. That's pretty close to what the calculator had given us for r squared before. So 0.9367. So remember that our coefficient of correlation, that was 0.97. And if you square that, 0.97 squared, now we rounded that, 9409, 9367. This was actually, I think that was I want to say that was 967. Let's see, stat, tests, I'm sorry, calc, and then 4 was our linear regression. Yeah, 9677, 968. So if we took the 0.968 and squared it, we get 937. So notice that negative 0.968 squared is 0.937. And that's what we're getting here, 0.937. So this is the coefficient of correlation r squared. So our interpretation here is that 93.67% of the variability, or the sample variability, is explained by the linear relationship between x and y. And then just a quick note here, if you do linear regression on your calculator and you do not get the r and r squared values, then you need to go to the catalog and turn diagnostic on to get your r and r squared. So to do that, you do second catalog here, and then you just scroll down until you get to the D's. And you'll see right there, diagnostic on. Highlight that one, press enter, enter again until it says done, and now it'll show your r and r squared.